Okay, today we're going to start the logic chapter. So before we start talking about logic, we might want to know what it is. Logic is the study of reasoning and it has applications in many fields, including philosophy, law, psychology, digital electronics, and computer science. So first we'll talk about statements and quantifiers, which is section 2.1. The building block of any logical argument is a logical statement, or simply a statement. A logical statement has the form of a complete sentence and it must make a claim that can be identified as being true or false. When evaluating the strength or validity of a logical statement, they must also consider the truth values or the identification of true or false of all the statements used to support the argument. While a false statement is still considered a logical statement, a strong logical argument starts with true statements. Let's see if we can figure out how this works. So determine whether each of the following sentences represents a logical statement. If it is a logical statement, determine whether it's true or false. The Buffalo Bills defeated the New York Giants in the Super Bowl 45. Well, first of all, is this a statement? It is a statement. It's a complete sentence. It's saying something. We can determine whether or not it's true or false. In the case of this particular statement, it is a logical statement, but it's false. So, logical statement. Let's make this a little bigger. There we go. Logical statement. And it is false. Okay, our second example here is Michael Jackson's album Thriller was released in 1982. Again, it's a full sentence. It's saying something, complete statement, and we can determine whether or not it's true or false. So it is a logical statement. And if memory serves me correct, this is true. And would you like some coffee or tea? Now, this is a complete sentence, but it's a question, and we can't determine whether it's true or false. So this is not a logical statement. So now let's talk about some symbols and symbolic form. Mathematics, we like to use symbols. Words can get quite confusing at times. So when analyzing logical arguments that are made of multiple logical statements, symbolic form is used to reduce the amount of writing involved. Symbolic form also helps visualize the relationship between the statements in a more concise way to determine the strength or validity of an argument. Each logical statement is represented symbolically as a single lowercase letter, usually starting with the letter P. So, write each of the following logical statements in symbolic form. The movie Gandhi won the Academy Award for Best Picture in 1982. No, we'll start with the letter P. That's all it wants. That's how we'd represent. We would typically, when introducing this, define statement P as the movie Gandhi won Academy Award for Best Picture in 1982. Soccer is the most popular sport in the world. Again, so go to the next letter, Q. Again, typically we would define our notation, our symbolic form in this fashion. Q is the statement soccer is the most popular sport in the world. And all oranges are citrus fruit. Again, we just give it an R. And we go like that. That would be how we define our logical statements. The next thing we come up with two is the negation of a logical statement. It has the opposite truth value of the original statement. So if the original statement is true, the negation would be false. If the initial statement is false, the negation would be true. So negating logical statements. Write the negation of each logical statement in words. It says here that Ted Cruz was not born in Texas. So what would be the negation of that? What would be, I'm not sure if Ted Cruz was born in Texas, but this says he's not. So what would be the negative of that would be simply Ted Cruz was born in Texas. Again, we're initially saying he's not. So to negate that, all we need to do really is take the not out. Okay, our next one here is Adele has a beautiful singing voice. So here we're going to use the word not to change it to the negation. And we'll add a quantifier in there as well. Adele does not have a beautiful singing voice. And same thing here. Leaves convert carbon dioxide to oxygen during the process of photosynthesis. So again, the negation. We'll use the word not again. Leaves do not convert carbon dioxide to oxygen during the process of photosynthesis. And there we have the negation. So again, that's a lot of words to write. I could have just said, this is P and this is not P. This is Q and this is not Q. And this is R and this is not R. Which brings us to the symbology. Symbol for negation or not in logic is the tilde, which is that little kind of curvy line. So not P, as I did above, is represented as the tilde and then P. To negate a statement symbolically, remove or add a tilde. Now, negation of a not P, is P. So symbolically, this equation is the negation of the negation of P equals P. So we want to write the negation of each logical statement symbolically. So this time we don't have to write the words out. So here we have the negation of P. So we want the negation of the negation of P, which as it shows here is simply P. Here we're dividing the statement Q as Adele has a beautiful voice. The negation in symbology would simply be that, the tilde and then the Q, and same thing here. There we go. So here we're given the statements Woody and Buzz Lightyear are best friends, and Wonder Woman is not stronger than Captain Marvel. I think this, so write the symbolic form of the statement Wonder Woman is stronger than Captain Marvel. Well, that is simply Q. And translate the statement into words. It doesn't make sense. It's already in words. Oh, Wonder Woman is stronger than Captain Marvel. And this is not, so that is Q. And I'm wondering if this wants this, not P. We'll go with that. So we'll define not P as Woody and Buzz Lightyear are not best friends. That's not clear, but I think that's what it wants. So that brings us to quantifiers. A quantifier is a term that expresses a numerical relationship between two sets of categories. For example, all squares are also rectangles, but only some rectangles are squares, and no squares are circles. In this example, all, some, and none are quantifiers. In a logical statement, the logical statements made to support the argument are called premises, and a judgment made based on the premises is called a conclusion. Logical arguments that begin with specific premises and attempt to draw more general conclusions are called inductive arguments. So let's draw some general conclusions. For each series of premises, draw a logical conclusion to the argument that includes one of the following quantifiers, all, some, or none. 1 plus 2 equals 3. 5 plus 6 equals 11. 14 plus 15 equals 29. Of these, 1 and 2 are consecutive integers, 5 and 6 are consecutive integers, and 14 and 15 are consecutive integers. Also, their sums, 3, 11, and 29, are all prime numbers. Prime numbers are positive integers greater than 1 that are only divisible by 1 in the number itself. What conclusion can you draw from these premises? Now, you're thinking all of them. So we're talking about adding consecutive positive integers results in a prime number. That's what we're looking at. But is it all of them? The- what about 10 and 11? That's 21. It's not prime. So it's not all, and it's not none. So we're going to adding some consecutive positive integers results in a prime number. A robin is a bird and lays blue eggs. A chicken is a bird that typically lays white and brown eggs. An ostrich is a bird that lays exceptionally large eggs. If a bird lays eggs, then they do not give live birth to their young. What conclusion can you draw from these premises? And the third one, what conclusion can we draw? Well, I'm thinking no birds give live birth to their young. Okay, how about the next one here? All parallelograms have four sides. All rectangles are parallelograms. All squares are rectangles. What addition conclusion can you make about squares from this premise? I would say all squares are parallelogram. Note, it's not possible to prove definitively that an inductive argument is true or false in most cases. Now, what about negating statements with quantifiers? So recall, negation of a statement will have the opposite truth value of the original statement. There are four basic forms that logical statements with quantifiers take on. You may have all A are B, some A are B, no A are B, or some A are not B. The negation of logical statements that use the quantifiers all, some, or none is a little more complicated than just adding or removing the word not. Now, the table below summarizes the four different forms of logical statements involving quantifiers and the forms of their associated negations, as well as the meaning of the relationship between the two categories or sets A and B. So let's look at our table here. So we have the statement, all A are B. An example would be all zebras have stripes, which is a true statement. The negation of this would be some A are not B. So the negation of all is some, not none. It seems a little counterintuitive, so be careful. Some zebras do not have stripes. Then we have some A or B. Some fish are sharks. Here the negation is no A or B, because some means there's one. So the only way you can get the opposite value of that is to say none, because some could also mean all. And here we would say no fish or sharks, which again would be a false statement. Then we go to no A or B. So, of course, the negation of that is simply some A or B. No trees are evergreens, which is false. Some trees are evergreens are true, is true. And then we have some A or not B, and the negation of that is all A or B. Okay, so given the statements, write each of the following symbolic statements in words. Okay, I have some apples are not sweet. So I'm guessing it wants to, this is saying this is the negation of P. So I'm assuming this wants the negation. So if some apples are sweet, we look at our table, some A or B. Here we go. No apples are sweet. And this would then be labeled simply P as a negation of not P. Now we're looking for negation of R, which is no triangles are square. So we look at our table here, no A or B gives us some triangles are squares. Okay? And lastly, we have S here, and we want to negate S. The statement is some vegetables are green. So we're going from some to no. So no vegetables are green. And that is the conclusion of section 2.1.